Okay, good morning, everyone. Today I will talk about independent and dependent events. This is section 11.3. Our objectives is to determine whether events are independent or dependent, and then to find the probability of independent and dependent events. Vocab today: what do we mean by independent events? What do we mean by dependent events? And then we'll take a look at conditional probability. So we say the two events are independent if the probability of A and B happening at the same time, well, if it's equal to the probability of A times the probability of B. Okay, so for two independent events, the probability of A and B equals the probability of A happening times the probability of B happening. So let's assume you have two number cubes, one red and one blue. A number cube has 6 possibilities. Okay, 1, 2, 3, 4, 5, or 6. Each number cube has 6 possible outcomes. So, if two number cubes are rolled, what's the probability of each cube showing 6? Well, the probability of like a red cube showing 6 is 1/6. And the probability of the blue cube showing a 6 is 1/6. So the probability that both of those cubes together show 1/6 is 1/36. The probability of A times the probability of B equals 1/36. Certainly, if I roll two cubes, one cube does not care or remember anything about the other cube. We like to say with independent events that the process has no memory. It's always a good way to look at it. The process has no memory. Or in other words, the red cube does not know anything about what the blue cube did, or vice versa. It has no memory. Each event has no memory. Okay, let's take a look at another one. Let's say here two integers from 1 to 8 are randomly selected. Okay, so there's 8 possibilities for each integer. So I randomly select an integer for the first one, and then I randomly select an integer for the second one. Certainly, the process, they're independent. So, the same number can be chosen both times. So I can choose either one of 8 numbers for the first integer or one of 8 numbers for the second integer. But the process has no memory. Whatever I select has for the first integer, well, the second integer, it doesn't impact or affect the second integer selection. So two integers from 1 to 8 are randomly selected. Then what's the probability that both integers chosen are greater than 2? Well, integers greater than 2 are 3, 4, 5, 6, 7, 8, so there's 6 of them. So the probability I choose an integer greater than 2 for the first integer is 6/8. 6 events divided by 8, which is my total sample space, or 3/4. So the probability I choose two integers where both are greater than 2 is 3/4 times 3/4, or 9/16. Again, each selection or each integer chosen only has a 6/8 or 3/4 chance. Probability is 3/4 for each integer, 6/8, 3/4. So again, 3/4 times 3/4 would give you 9/16. The events are independent. The probability of A and B happening is equal to the probability of A times the probability of B. Again, sometimes complements. Remember, complements of the probability of not an event is equal to 1 minus the probability of that event. So here's an example. In a class of 30, 12 to 17 teenagers, what's the probability that at least one has used marijuana? If 53% of all teens 12 through 17 has used marijuana. So I have 30 students in the class, and it could be at least one. So I could have one that has used marijuana, or two that have used, or three that have used, and four, yada yada yada, all the way to 30. Well, what's the probability that at least one? Well, the best way to get at that is to use the complement. I can say, well, what's the probability that at least one has used marijuana is equal to 1 minus the probability that none has used marijuana. Okay, taking the complement. 1 minus the probability that none has used marijuana. Well, the probability that none has used marijuana is 47, or one person or someone has not used marijuana, or anyone. The probability that that teenager has not used marijuana is 47% if 53% of all teenagers reported using marijuana. Okay, so then 1 minus the probability that none use marijuana is 1 minus 0.47 raised to the 30th, because it should be independent that if one teenager does not use marijuana, that should be independent of any other teenager not using marijuana. Okay, they should be independent events, assuming they're independent events. That the non-usage of marijuana for one teenager has nothing to do with the non-usage of marijuana for another teenager. They're independent. So the probability that at least one has used marijuana is 1 minus the probability that none of them, and the none of them, again, they're independent, 0.47 times 0.47 times 0.47, 30 times. They're all independent events. So the probability that at least one has used marijuana is almost 100%. 1 minus 0. At least one has used marijuana. It's 99.9%. So that is independent or independent probability. They're independent of each other. The process has no memory. One event does not care about what the other event did. Now let's look at dependent probability, where one event cares about or remembers something about another event. Okay, here we say the process has memory, or process has a memory. So if events are dependent, they occur together, then the probability of A and B equals the probability that events A and B, if they occur together, the probability of events A and B occurring the probability you have to divide by the total sample space. So I'll show you what I mean here. Okay. Dependent probability. They happen together. All right. The process has memory. One thing depends on the other. One thing depends on the other. Okay, so example, 2 number cubes are rolled, one red and one blue. Find a probability that the red cube shows a 1 and the sum is less than 5. Okay, and the sum is less than 5. The key word here is and anytime you see that and, you know we're talking about the total sample space. Anytime you see and, independent probability, we have to consider the total sample space. So let's look at this one. Find the probability that the red cube shows 1 and the sum is less than 5. Well, we have to list all the ways in which the sum is less than 5. And I'm going to assume that this first number here is the red cube. So let's list all the ways in which the sum is less than 5 when you roll 2 cubes. Well, You have 1, 1, 1, 2, 1, 3. I've exhausted all the ones. Now I have 2, 1, 2, 2. I've exhausted all the 2's, and then 3, 1. So those are all the outcomes where the sum is less than 5. Now, let's pick when the red cube shows a 1. Well, there's only 3 outcomes where the red cube shows a 1. 1, 1, 1, 2, 1, 3, when the sum is less than 5. Okay. So the probability that the red cube shows a 1 and the sum is less than 5 is we have 3 out of 36 outcomes. Remember, there's 36 possible outcomes when you roll 2 cubes. 6 times 6. So the probability will be 1/12, 3 over 36. Dependent. So you see that they're dependent. You have to have a sum of 5 and the red cube shows a 1. They're dependent. One thing depends on the other. But in this case, and, when you see and, you have to divide by the total sample space. The total sample space. So let's look at another one here. 2 number cubes are wrote. What's the probability that the sum is 7 and 1 cube shows a 3? All right, so again, we have to list all the ways in which the sum is 7. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. And then how many of those where 1 cube shows a 3? Well, we have 3, 4, 4, 3. So the probability that the sum is 7 and 1 cube shows a 3, again, we see and, so we have to consider the total sample space. When we roll 2 cubes, it's 36 outcomes. So the probability that the sum is 7 and 1 cube shows a 3 is 2 out of 36, 1/18. So that's dependent probability. Now we'll look at conditional probability. So a conditional probability is one event is conditioned on another event happening. So we say events B or event B given A, but we have to now change the sample space. It's going to be a reduced sample space because B has happened given that A has happened. B happened given A. B given A. So for example, let's say here you're riding your bike and you fall off your bike. Well, what's the probability that you'll fall and hit your head? Okay, what's the probability if you're riding your bike, you'll fall and hit your head? Well, falling and hitting your head is conditioned upon you riding your bike. Okay, so if I just said, well, what's the probability if you just fell, if you weren't riding your bike? Well, that's going to be different. That's going to be different than the probability that you fell and hit your head if you rode your bike. Okay, you would think that if you're just walking down the street, what's the probability you would fall and hit your head? Well, that would be a lot less than the probability than if you were riding your bike and you fell and hit your head. Okay, so the sample space is reduced. So let's take a look at this. 2 number cubes are rolled and 1 red and 1 blue. Okay, find a probability of a red cube shows a 1 given the sum is less than 5. Okay, so we have more information here. I like to say with conditional probability, we have more information. We have more information. Oops. We have more info. Okay, so now we know that the sum is less than 5. So that would be my reduced sample space. We know that the sum is less than 5. Find the probability that the red cube shows a 1 given the sum is less than 5. Okay, so we have to list all the ways in which the sum is less than 5. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and then 3, 1. Now, if I say the red cube is the first number, well, there's only 3 outcomes for the 6. So 1, 1, 1, 2, 1, 3. So the probability that the red cube shows a 1 given the sum is less than 5 is 1/2. Given. Let's look at another one. 2 number cubes are rolled. What's the probability that the sum is 7 given 1 cube shows a 3? Okay, so we have to list all the ways in which one of the cubes shows a 3. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. That's for the first cube shows a 3. And then now let's when the second cube shows a 3. 1, 3, 2, 3. I've already have 3, 3, and then 4, 3, 5, 3, 6, 3. So here I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 11 events in my reduced sample space, and only two of them have a sum of 7. What's the probability that the sum is 7 given 1 cube shows a 3? 3, 4, 4, 3. That's my event space. Those are my favorable outcomes. So the probability will be 2 over 11. So you see, with given you have a reduced sample space, we have more information. We know that one of the cubes showed a 3. 2 out of 11 would be the probability. So let's look at this in terms of a table format. The table shows domestic migration from 1995 to 2000. A person is randomly selected. Find each probability. Find the probability that someone is an immigrant given they are from the West. So the reduced sample space given they are from the West. Well, there's 5,320 folks who are from the West. Then how many of those were an immigrant? Well, 26666. So the probability that someone is an immigrant given they are from the West is 26666 divided by 5320. 50.1%. Find the probability that someone from the West, someone is from the West, given that they are an immigrant or emigrant. Okay, so given, so you have to total up all the immigrants. And now that they're from the West, well, let's see here. So 2654 were from the West. So that probability is going to be 2654 divided by 11656, or 22.7%. So always with given, you have a reduced sample space. So the first one, I looked at the sample space given they were from the West, the reduced sample space was 5320. And then the second one, given they are immigrant, well, the reduced sample space was 11656. See, it wasn't all the total. It wasn't the total of everybody. It's a reduced sample space. Now, if I throw and in there, find the probability that someone is an immigrant and here's the key, and is from the Midwest. With and, we have to consider the total sample space. Total. We have to consider the total of everybody. Okay, so remember I said back up here. When you have and is an operative word, you have to consider the total sample space. Total sample, and you have to consider the total sample space. With given, you have a reduced sample space. So find the probability that someone is an immigrant and is from the Midwest. Well, up here you'd have to total everybody, and so the total of everyone is 23311. 23111. So that's my total sample space. But now we have to look to see where their immigrant and is from the Midwest. What did I say? An immigrant and from the Midwest. They're an immigrant and from the, oops, did I say West or Midwest? Midwest, right? So that should be 2-4. An immigrant and, so immigrant and from the Midwest. 2410. Did I have 2410? That should be 2410. Right? So I better change that percent. I thought I had West. It was from the Midwest. 2410 divided by the total. And that would be 10.3%. Okay, so again, the operative keyword there was and. And you have to consider the total sample space. Sample space is all. Let's look at two more examples. 2 cards are drawn from a deck of 52 to determine whether the events are independent or dependent. Find the probability. Selecting 2 hearts when the cards are replaced. Well, they're independent events. Selecting the second card does not remember what happened when you select the first card because we replaced it. It's like we're starting all over again. They're independent. So selecting 2 hearts. So we have a total of 52 cards in a deck, if you've ever played cards. And then we have 13 hearts. 13 hearts. 13 in each suit. 13 spades, 13 diamonds, 13 clubs, 13 hearts. 52 cards total. So the probability of selecting 2 hearts when the cards are replaced. So we have 13 out of 52. You select the first card, you put it back. The process has no memory. You select another card. The probability of selecting a heart is 13 out of 52. Well, that's 1/4 times 1/4 is 1/16. And then now, selecting 2 hearts without replacement. Well, they're dependent because now the process has memory. Okay. The second time you select a card, it remembers what happens the first time because you're not replacing it. You're not replacing it. The process has memory. So the probability of selecting a heart the first time is 13 out of 52. You have 13 hearts out of 52 total. But now you don't replace the card. So you have 12 hearts left out of 51. See, the process has memory. Okay, 12 out of 51. And if you reduce that, you'll get 3 out of 51. All right, so 4 goes into 12 3 times, and 4 goes into 52 13 times, and then 13 into 13 once, and 13 into 13 once, and we get 3 out of 51. So you see that the process has memory.